Tuesday Geometry, going over math packet number 4 with you. This is due Tuesday the 30th, as you can see there. But to allow you an opportunity to turn in early for me to check over, if you give it to me the 29th, that Monday, you'll get it back Tuesday, and you won't have to turn it in to me until Wednesday. So if you turn it in Monday, it's due Wednesday to give you a day to make corrections. If you don't turn it in to me Monday, then it is due like normal on Tuesday. If I don't answer one of your questions that you have in this video, please don't hesitate. Send me an email, and I'll do my best to get back to you and help you over break. So, two rectangles have perimeters of 144 centimeters. What is the greatest possible difference between their areas if the length and width of both rectangles are integers? So, essentially, we got two rectangles here. We'll assume one is larger than the other. One's going to kind of have to be if we're looking for the greatest possible difference of their areas. And let's call the base of each rectangle, or the base of each rectangle x, and the height of each rectangle y. Okay. Now I'm labeling these with the same variable, which is cheating in a way, because they're not the same. Obviously, if x was the same in both rectangles, then it'd be the same size, it wouldn't really make sense. But what I'm getting at here is that for each rectangle, 2x plus 2y has to equal 144, right? That's what perimeter is. It's the sum of all the sides. Each rectangle has 2 of a base and 2 of a height. And so 2x plus 2y equals 144. And if you want to use, I suppose using b and h for base and height would make more sense here, but whatever. And so for starters, you're kind of going through and you're solving this equation. What values for x and y make this work? If x is 20, then what is y to get 144? And you could approach this from a graphical sense to where maybe putting this in a slope-intercept form, and then looking at the equation of the line. You get all those combinations for x and y that get 144. But essentially, what base and length will give you the greatest area? What base and length will get you the smallest area? Because the question is, what is that greatest possible difference? Okay, so get you started at least anyway, and maybe guess and check is the way to go here. Just plug in, see what happens, look for a pattern. But if you have any questions, you can shoot me an email. If there are 15 people at a party and they each shake hands with everyone else once, how many handshakes are there altogether? This is a classic math question. Did I just admit you could probably Google this? I think I just did. But how many handshakes are there total if 15 people each shakes hands with each person else once? And what you have to make sure you do not do is count each handshake more than one time. Let's count each handshake just once. For example, person number 1 shaking hands with person number 2 is the same handshake as person 2 shaking hands with person 1. We actually kind of had a question like this, if you remember back in the basketball league question. Each team in one division plays every other team in their division twice, and then each team in the other division once. And we had talked about not counting games more than once. So what I want to do is, person number 1 walks in, shakes hands with everybody else. How many handshakes will person number 1 have? Well, since you can't shake hands with yourself, there are 14 other people for that one to shake hands with. Okay. Person number 2, right? How many handshakes will person number 2 have? Well, person number 2 will also have 14, but because we already counted the handshake between number 1 and number 2, there are really 13 new handshakes happening here. Person number 3 comes in, 14 people for person number 3 to shake hands with. But again, because we already counted the handshake with 3 and 1 and 3 and 2, there are only 12 new handshakes happening. Okay, so I think you can kind of see a pattern developing here, and you can take it the rest of the way for the number of total handshakes at this party. 5-card challenge. Don't need to spend much time on this. Make sure you're getting all 21 points or more. At least one equation using all 5 cards. You should be pretty familiar with that setup by now. This one, calculate the percentage of the figure that is shaded And this did not copy off very well, I'm realizing now. The shaded section is this. Of course, I'm using the thinnest possible marker here. The shaded section is this area here. Okay, the entire figure includes everything that's contained within the solid line and this semicircle that is contained with the solid line and the dotted line. Okay, so the figure is this half circle with a diameter of 8 here, and then also that entire shaded section enclosed within these solid lines. And so what I want you to notice here, all the circles that we have, that's going to be kind of my hint to you on this one. Notice the circles. We have a small half circle here with a diameter of 4. We have a medium-sized half circle here, which is not part of the shaded region, with a diameter of 8. And then we have big one here, that large half circle, right, with a diameter of 12. So how can you use those half circles to kind of manipulate the pieces here so that you get that area of the shaded section there, okay? Lots of adding and subtracting with these half circle areas, which, again, now I gotta flip back to my marker. The area of a circle, pi times the radius squared. Because we're only dealing with half circles, we're going to want to divide that by 2 to get the area of half circles. Next up, we have our pattern block question. This is another one that you need to create a graph for. Feel free to share that with me on the Google or print it out and bring it in. But you're filling out the table, and as we've seen in previous patterns, starting with that total blocks section might be the best way to go here. In figure 1, it's easy to see we've got 1 block there. Figure 2 is a 2x3 rectangle, which gives us 6. Figure 3 is a 3x5 rectangle for 15. And figure 4 is a 4x7 rectangle. I can't really erase this, I'm going to scratch out, which is 28 total blocks. And then we can see also that, we got 1 blue in figure 1, 1 blue in figure 2, 1 in figure 3. And then even though we're adding 13 blocks in figure 4, we want to write the total number of blue blocks, which is 14. The 13 that we added plus the 1 that we had originally. And we can carry this 14 down another 2 figures because we only add another row of that same color every 4th figure. Okay? And then we kind of fill in what else we know. No green blocks in the first figure, 5, and that carries down through the next 3. No red blocks in the first, no red blocks in the second, and then we get 9, and we know that carries down for 3 as well. Okay? And then once you develop this pattern in the total blocks, since you only have 1 empty slot per color for each row, once you carry them down as far as you can go, then it just becomes subtraction to fill that in. And so the pattern then in the total blocks here is key. And we started with a 1x1 square to get 1 block. Then we went to a 2x3 rectangle for 6, a 3x5 rectangle for 15, and a 4x7 rectangle for 28. Maybe you're seeing a pattern develop. If not, take a closer look at the multiplication that I just wrote down and see what you can come up with there. But I would start with the total blocks and then fill in the other colors as needed. And then don't forget to do the graph as well. Next one, surface area. We've got a pyramid here. And a pyramid, when you fold it out flat, it's got that square base, right? This is an 8x8 here. And then it's got a triangle coming out from each side, okay? Also, each with a base of 8, and each with a height of 16. So recall that the four-dimensional area of a triangle is base times height divided by 2. And all these triangles are the same size because the base of our pyramid is a square. So once you get the area of one triangle, you really have the area of all 4 of them. And then add in the area of the square base, and that will give you the total surface area, right? The surface area is the sum of all of the areas of the surfaces. Okay, that's kind of how to go about that. Then we come across a pyramid with volume. And the relationship between a pyramid and a rectangular prism that it comes from is that if you were to imagine, I'm going to draw this poorly, I can almost promise you, but if you were to imagine come down like this, that look very prismy? It doesn't, does it? Anyway, if you were to imagine a rectangular prism that you cut a pyramid from, that pyramid is always going to be 1/3 the volume of the original prism. So when we start to write this formula for a pyramid, you should recognize, hey, base times width times height, that's the formula for the volume of a rectangular prism, like for a normal box. So then for a pyramid, it's just that volume divided by 3. Kind of like, the area of a triangle is base times height divided by 2. The triangle is half a rectangle. There's that relationship there. The same thing exists here, right? So for this particular pyramid, we're taking 10 times 8 times 6 and dividing that by 3. You can finish that out there. Then your question, geometry, the slant height, which is this, not listed here, but the height of a triangular face. So on the last page, actually, when we dealt with surface area, we needed that slant height. That slant height is 16 feet. That's the height of one of the triangular faces. Whereas the height of a pyramid for volume, notice that 6 goes from the top of the pyramid down to the middle of that square base. It's not the slant height. It's not the actual height of one of the triangular surfaces. So the slant height is 8 inches for the triangle with a base of 10 inches and 7 inches for a base of 8 inches. So just draw this in here, okay? For the base of 10 inches, our slant height, right, which is the height of the triangle, is 8. And 7 inches for our other base. So this is the height of the triangle, that surface, and that is 7. What is the surface area of the pyramid? So different than the pyramid you saw on your surface area page, these triangular surfaces aren't the same. Okay? Just like a rectangle has 2 pairs of opposite sides, a triangular prism, a pyramid from a rectangular prism will have those 2 pairs of congruent triangular surfaces, if you get what I'm trying to say. So a little bit different calculation than you did on the surface area page. You need to find both sets of triangular faces for the area, and then that base is a rectangle there. But surface area is your ultimate answer. Math exploration. Let's talk about George Alexander Pick. And no, it's not a typo. Mr. Pick did not have an E at the end of his first name there. Here's a nifty theorem you can use to save time and energy when asked to find the area of a polygon that's been placed on the graph paper and its vertices that fall on grid points, because we do this a lot, right? Consider the following. To find the area of the polygon, we'll do this in black here because I already got colors. Okay. Count the number of interior points, I, in red. So notice how on this polygon here, we've got a certain number of interior points inside the polygon that have been labeled in red. And it looks like there are 1, 2, 3, 4, 5, 6, 7 of them. Okay. Then count the number of boundary points, which are where it lands on coordinates on the outside of the figure, and they've been labeled in green. So 1, 2, 3, 4, 5, 6, 7, 8. Right? Pix Theorem says that the area of this figure is going to be the interior points plus the green, the boundary points, divided by 2 minus 1. And notice the order of operations here. It's not the sum of I plus b divided by 2. It's just b divided by 2. Okay? So in this case, we got the values plugged in here. Okay? 7 plus 8 divided by 2, or 7 plus 4, is 11, minus 1 is 10. So your job now is to find the area of each polygon below. Which one should we do? You always ask for the first one. So we'll do the first one here. So similar to the example, we will label our boundary points in green. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 boundary points. Okay? Interior points. We will label those in red. We've got 1, 2, 3, 4, 5. Okay? Now, using Pix Theorem, right, the area will be equal to, go back to black here. Okay, the area equals I plus B divided by 2 minus 1. In our case here, that would be 5 plus 18 divided by 2 minus 1. Or 5 plus 9, 14 minus 1 would give us an area of 13. I picked an easy shape like this to start with because we can easily verify this formula works by simply counting the squares. There's no diagonal sides here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It works out, right? I can't do that with this next one because it's got a whole bunch of diagonal sides. But you can still use Pix Theorem. So you're going to go through and you're going to count the number of boundary points, right? All these here in green, where it hits a dot, okay? Then count all the interior points, all those dots inside the figure. Like that one, they're already kind of red for you there, but make them a little more obvious for you. That's not one, right? I skipped over that because that is a boundary point, okay? And then apply Pix Theorem to get the area, right? Got a couple other more fun ones for you to do there. Pix Theorem. I'm so glad I picked it. Okay. Possibility diagram number 2. You spin 2 spinners, each with 8 equally sized sections, and you need to use a possibility diagram for this. Some of you are not doing that, and you need to. So 1, 2, 3, 4, 5, 6, 7, 8 to represent the sections on our first spinner. And 1, 2, 3, 4, 5, 6, 7, 8 to represent the sections on our second spinner. And it says, what is the probability of spinning the same number both times? So that's one thing. A sum that is prime, or a sum that is a perfect square. So you're focusing here on the sums. Okay? 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. And so on up the line. It's going to be the same thing going along the horizontal axis here. Then 2 plus 2 would give us a 4. 2 plus 3 is 5, 6, 7, 8, 9, 10, and so on. You're going to fill this out, right? And so you'll get a total of 64 possible outcomes, right? 8 by 8, 64, 8 times 8 there. And so your successful outcomes are the same number both times. So really, you're going to have a diagonal of successful outcomes right through the middle there. A sum that's prime, so know your primes, and then a sum that's a perfect square. Be careful not to count the same thing more than once. For example, you would not count this 2 for both the same number twice and a prime number. It falls in both categories, but it's only one outcome. So you only count it once. Same thing with the 4. Same number both times, and 4 is a perfect square. Falls in both categories, but only one outcome, so only count it once. Okay? And then your probability out of 64 there. Your number of successful outcomes divided by 64. The Tetris one, you know how this works, no explanation needed. And finally, a logic puzzle here. It says, at the city's new art museum, one of the main galleries features 6 paintings of different subjects on a wall arranged from left to right, numbered 1 through 6. Figure out the order in which the paintings are hanging on the wall. Okay. The first clue says I almost said horizontal, like horizontal. The horizon painting is directly between the pond and ship paintings. And so what you need to remember here is that rarely will these clues ever get you the right answer, but they'll allow you to eliminate wrong answers. If we know that the horizon painting is between the pond and the ship paintings, that means the horizon painting can't be on an end. Right? Because then it's not between. If it's the first painting or the 6th one, it's not between any. Okay? So we can eliminate the horizon painting as the first and the 6th. Right? So that's the kind of thought process that you want to have for these. And then as you eliminate, you'll realize that things, kind of by elimination, you discover the correct answers, and then you can go from there. But that's how you want to tackle these logic puzzles. Our next unit actually is going to be all about logic, and so we will have some of these to do as part of our main curriculum also. But that's math packet number 4. Like I said, if you've got any questions, don't hesitate to contact me. Have a great weekend, a great Thanksgiving. Be well, stay healthy, gobble gobble, and don't forget to like and subscribe.